Thank you very much, Dan. And thank you, everyone. Thank you so very much. Yes, this is absolutely a challenging talk to always give. Fortunately, I like challenges, and I boldly go in those places. So yes, we are definitely in a phase of science at this point where everything's very rapidly changing. I like to joke to my students that when I was born, there were 9 planets. Then Neil deGrasse Tyson came along and kicked one of them out of the club. And so now we're down, Pluto's out, and we went to 8. But all of a sudden, everything really changed. And we know, I guess I've heard that some of our previous speakers have discussed this enormous explosion of planets that we've suddenly been finding. Something that scientists had certainly hypothesized, something that if you cornered a physicist in a dark room somewhere and said, tell me the answer, we're going to say, yeah, there are definitely other planets out there. But we like to have evidence before we talk about things. And that's where the temerity comes with this discussion, because as much as suddenly this is a game-changing moment that we're finding all of these new planets, the discussion of life is still incredibly challenging. And it leads me to this image that I have in front of you now. And this is that famous image from back in the 1990s where we cracked open an asteroid and said, hey, look, life. And you cannot do that in this field without knowing that you have opened up a major can of worms, that there is going to be science flying at you from every which what direction. You have geochemists saying this is obviously something very simple. This is a geochemical idea. You have biologists saying no, geochemistry can't form like this. It cannot produce shapes and forms like this. And that debate rages on. And it's been almost 2 decades since this debate began. And we have literally marched nowhere in that discussion. Of course, it's a very exciting time. We've dropped an SUV on Mars recently, and it's one of its primary jobs. Make no doubt, we get to joke, it's huge. The first thing we sent to Mars, Sojourner, was literally this big. You could hold it in your hand. It would look like an RC car that you could buy at KB Toys for like 10 bucks. It lasted several months and did some science. Okay. We had Spirit and Opportunity. Spirit is toast, but Opportunity continues on, and they're doing great work, or one of them did great work. The other one continues to do great work, but now we have Curiosity, and it's well named, because one of the prime reasons that we sent Curiosity to Mars was simply to find life, to try and to start answering this question. So what's interesting, however, is of course we have Carl here, and Carl is always pretty much the modus operandi for anything I do, but he's standing next to the Viking lander. Now, for a lot of the people in this room, you weren't born yet. For some of the people in the room, you remember this moment when Viking landed. And we did a number of tests. Part of the Viking mission, again, we named it well. The Vikings went and probably got here before, the Pilgrims did. They found things, and that was the idea of sending Viking 1 and Viking 2 to Mars. And we had many, many different tests, 3, that were going to try and find life on Mars. And we concluded at the time, not good enough. The rigors of science are immense. Basically, unless we're at about 99.5, we're not happy. And if only our government worked that way. We have a wee bit more rigor. Fortunately, though, science evolves. And not only has science evolved since the 70s when all of this happened, but further, our computational power has evolved since that time. I remember my computers in the early 80s. I also remember programming on cards. It's gotten a wee bit better at this point. I have a 128 gigabyte thing the size of my thumb. My original computers had no hard drive. So we went back and we analyzed the results from Viking, and lo and behold, suddenly we have upgraded these decisions. There are scientists now in this country and around the world who are willing to say that Viking may have actually detected life at that time 30 years ago. But that we have not, again, reached that 99.5% certainty rate where scientists are going to put their careers on the line. Again, temerity of having this conversation. To say, yes, we have definitely found life. Because we cannot say that. Again, it's in that, well, maybe we might have kind of sort of found something. Maybe. If. So we need to do better. So this leads us to the idea of Frank Drake and the infamous Drake equation. I cannot use that word strongly enough, infamous, because this is one of the most used and abused pieces of science I've ever seen. And it's why people have such temerity to go into this conversation, because no matter how many times I caveat something, the room will say, he said there's life out there. Well, we're going to try and make sure that you understand everything about that. The Drake equation itself is very, very simple. It's in front of you. And we might say, okay, that's kind of a long equation. But it's not so bad, because mostly it's just a bunch of numbers. And we're going to discuss these numbers tonight and build up what we want. But the Drake equation says one thing. How many galactic civilizations do we feel are probably out there? How many other civilizations like us are out there? Now let me be clear. Anything we found on Mars, we're talking about very, very small life. We have never at any moment had any reason to believe we have ever met anything like us. And that's what we're truly looking for. Yes, it'll be incredibly exciting and incredibly important for us to find that small scale life. That's an enormous step, and we'll talk about that in a little bit. But we're not looking for that per se. We're looking for you. We're looking for someone to have a conversation with, someone to tell us all the information they know. We're scientists. We want to trade notes. We want to publish papers with each other. We want collaborators. So what we have here is an equation that says the number of civilizations in my sky is equal to a whole bunch of numbers multiplied together. So we start at the beginning, n sub star. It's the number of stars in my galaxy. Well, it's a big galaxy. The Milky Way is certainly not a small galaxy. It's not even certainly an average galaxy. It's a fairly large galaxy in the grand scheme of things. It's about 130,000 light years across, meaning if I was traveling at the speed of light, it would take me longer than humanity has been civilized, by an order of about 100, in order to get from A to B. We have about 400 billion stars in this galaxy. We might note you are there. We live in the boonies. We're kind of far out, and we're going to find out that that is actually a very, very good thing. But the first place we need to start, of course, is to say the star that you're going to form around is very important. And that we have several different types of stars. They're not all going to be like our own. Fortuitously, most of them spend most of their lifetime on what we call the main sequence, and we're going to caveat this discussion there and say we're only going to deal with main sequence stars. And here they are. In reverse order in this case, we go M, K, G, F, A, B, O. And we get larger, more massive, hotter, and more luminous with each step up this scale. Our star, of course, is a G2V star, which means we're here. We're slightly bigger than a K star, but not much. And we're in the main part of our life. We've got about 7.5 billion years left in our star's lifetime. Well, you might imagine that if I were to take our star and replace it with one of these O-class stars, we might have a problem. A very severe problem. That our atmosphere might vaporize, our water might vaporize, and you too would vaporize. So we can't just form life around any of these stars. It turns out that not only are they more luminous, but again, we're in Florida. We know a lot about ultraviolet light here. These O and B class stars especially produce copious amounts of UV light. We're well aware of the fact of what that does to biology. It leads to all kinds of mutations and cancers. We do not think that life is going to have an easy time forming around one of these stars. They're simply going to be too luminous, too much ultraviolet light. It's going to be very hard for life to survive in one of these places. Fortuitously, there are very, 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 very few of these stars. They actually make up about 0.1% of all of those stars that we've discussed, the 400 billion that make up this galaxy. So we'll say none of them between friends. Well, let's build up a little bit of an idea of scale, because again, one of the great difficulties of the physicists, especially the astrophysicists, is that we deal with such titanically large numbers that when I have a conversation with a great crowd like you guys, you get lost, because I say there's 17 zeros after this number, and you go, whoa. Because the human brain kind of evolved only to handle a small number of zeros, about 5 tops, and that's a small number for us. So we can start going through some of the familiar things, Mercury, Mars, Venus. We'll get back to Mercury in a little bit. Home, you are here once more, in case we didn't know. We can work our way out to Neptune, which is a bit bigger than Earth, but really not so much so. We get to Saturn, Sun's rings. We go to Jupiter. And you don't get to objects that are terribly much larger than Jupiter. In fact, if I kept stacking more and more mass on Jupiter, it's not going to get terribly much bigger. But we go to Sun and say, oh, that's 100 times larger than Earth. And it's a dwarf star, well named, as we're about to find out. As we go to some of these larger and larger stars. We're still at the babies. Don't worry, they get bigger. So we've got time, don't worry. We're not there yet. Give it time. One more. Did I say one more? Because I mean one more still. We need to get to VY Canis Majoris, the largest star that we currently know about in our night sky. And again, we're talking about numbers that are so large that your brain just is going to just have a seg fault trying to figure this all out. So this is great. I like this video because first of all it says, there you are. And it says, okay, let's try and envision this in our mind's eye. Let's try and get around this 2.8 billion kilometer object. So we're going to get in a passenger plane. We've done this, going at 900 kilometers per hour. It's a good pace, not too fast, not too slow. And we're going to take a ride for 1,100 years to go around this star. And we start to get an idea of what we're talking about. This is not a place that you would ever want to call home. It's just going to be too big. So we're left with 400 billion habitable stars for Earth-like planets to crop up on. Next, we have to deal with another problem. You can't just be anywhere in our galaxy. It turns out that if you're too close to the center, there are a lot of supernovae in there, it's a lot denser, there's a lot more radiation coming from that region. And again, you're simply not going to be able to survive. We don't think life is going to be able to thrive if you're too close to the galactic center. The same way, if you're too far from the galactic center, you're lacking a lot of these what we call heavy elements. Astronomers are funny, we say the universe is made of hydrogen, helium, and metal. And we say you're missing those metals, carbon, nitrogen, oxygen, iron, magnesium, things that you need to form life that we simply just don't have in these outer reaches of a galaxy. So unfortunately, this is limited actually down to about 10% of the stars that we originally had available to us. So we're down to about 40 billion stars. I'm feeling still confident because it's 6 times more than we have people on the planet, but we've got room to go. So we have 40 billion stars in our galaxy in which we could maybe, possibly, you're going to hear the caveats throughout the night, I'm a lawyer on this one, where we might find life. We say, okay, F sub p, that's what's next. The fraction of those stars that have planets. Now again, 10 years ago, 20 years ago, where I have this conversation with you, I'm stuck immediately into a corner. We know there are 9, 8 planets around our sun, and we know nothing else. We assume, again, astronomy professors will tell their students that there will always be debris from when you make a star. The debris is usually going to become a planet. It's certainly what we believe happened here in our solar system. And it's somewhat intuitive to believe that you should have planets just about everywhere. But we had no proof. Again, we are scientists. We must have proof. Well, that's been a changing game. We've been finding lots and lots and lots of exoplanets that we'll discuss later in this game. So for this, I'm going to be optimistic. I'm going to tell you that probably half of these objects, and this is extremely conservative, that number is realistically probably very close to 1. That most stars will have something orbiting it. It's going to be very hard, in fact, to have a star all by its lonesome, but we'll hedge our bets. We'll say 50%. So we're down to 20 billion places where we can find life. We're still doing very well. We get to that n sub e term. Okay, that's going to be the number of Earth-like planets. And we look here. That's not an Earth-like planet. That's Saturn. Duh. But if we look carefully, oh, we can't really see it. We can barely see it here. I'll help you. There's Earth. That little dot, ever so faint, actually might show up more nicely in this image. That's Earth. We're looking for that. We're looking for Earthrise. Again, as much as we're interested in small life, that would be a game changer. That would be enormous science, Nobel Prizes, interesting science. We really want to find, again, large-scale life. We're looking then for Earth-like planets. Because in the field of astrobiology that we're discussing, there's a big problem. We know that physics here is physics there is physics everywhere. We know that math here is math, there is math everywhere. We know chemistry here is chemistry, there is chemistry everywhere. Because we can check. Because we can observe using telescopes and we can check these fundamental laws. And we know, of course, they're the same everywhere. Biology is the weak link. Because we cannot see life forms anywhere else. We don't even know that they exist. And so we only know life as we know it here. But just like everyone in this room is related, if you go far enough back, every single life form on this planet is most likely related if you go far enough back. And thus we have a data set of 1. And in science that is completely unacceptable. because we can say nothing from it. Because we're all related, we can't say, this is of course the way that all life forms. We might in fact find an alien civilization that completely defies all of the biology we've ever studied here on the planet. Or it might fall into lockstep with us. We just don't know. We have no way to test. So we're going to assume that large-scale life is going to need the same things that we have needed all along in order to get to this point in our development. And so we're going to say we need water, we need an atmosphere, and we need energy. And those are going to be the big caveats. And it's got to be just so. Because we have this idea of a Goldilocks zone. Not too hot, not too cold, just right. In fact, it turns out that if I have a different kind of star, my situation changes. If I have a big star, one of those F, A, O, and B stars, like up top, what I'm going to have is a far out habitable zone, but it's going to be very wide. If I have a star like our own sun, it's going to be closer in, but narrower. And if I'm at a very cool star, like an M-class star, which make up 75% of the stars in our galaxy, it is going to be very close to its star. And it's going to be in a very thin region to have liquid water, which we believe is the #1 thing to our finding life. But we're looking for Earth-like planets. And so we can only assume they're going to randomly fall into this pattern. But we're not just looking for planets, because when we look at our solar system, we say, Earth, clearly, okay, we're here, life is here, this is good for life. Duh. We have to go a bit farther out. Venus is hell. Venus is the hottest planet in our solar system. There is molten lead on the surface of Venus. It is not a happy place. You are not going to find life there. Mars, on the other hand, is slightly farther out. It's a little too cold. Its atmosphere is barely there. It got killed early on in the early solar system, has no magnetic field or no appreciable magnetic field. And so it wasn't too conducive for life. But remember, we've spent a lot of money to land an SUV there. We still think there's life there. I would bet my bottom dollar there's life there. But again, small. Marvin the Martian is not cropping up anytime soon. But that's our planets. We can go to Jupiter and Saturn, Uranus, Neptune. These are gas-like planets. If we're looking for stuff like us, they simply don't live there. There's no way they can live there. There's no water that's available to them. The gases are incredibly toxic. We could talk, as Carl Sagan did, about the possibility of other life forms on those planets, but that's not the crux of this talk. So we're going to say those aren't viable to us, except in the inner solar system, there is, I like to say, one moon. There are 3. Mars has 2 asteroids it captured at one point, Phobos and Deimos, and we call them satellites. But when we go to the other planets, they have lots of them. There are about 167 moons that I know of currently in our solar system. One of them is larger than one of our planets. Titan seems larger, but it's only because it has an extremely appreciable atmosphere. If we take away that atmosphere, it is ever so slightly smaller. But what we can see here is, okay, if we're calling Mercury a planet, first and foremost, you see the Pluto issue. But secondly, we say, okay, there are some large objects in our solar system. Well, what if we look at the case of Epsilon Andromedae, a Jupiter-like planet that we know orbits a nearby star? Jupiter has, as far as we currently know, 63 moons. 4 of them are huge: Ganymede, Europa, Io, and Callisto. But there's still a lot more. There is potential for these Jovian planets where we couldn't live on that planet proper to have a moon that could easily be Earth-like. So bear that in mind as we go. So as I get back to my Drake equation, I'm going to guess that n sub e is probably about 2. So good, we've gotten rid of the problem of 50% of my stars don't have planets. We're back to 40 billion. Awesome. I like having a larger number here rather than a smaller number. At this point, we are about to step right off the cliff, because things get harder from this point out. We start to leave science. F sub L is the fraction of those Earth-like planets where I can actually have life. I am going to argue for you tonight that that should be probably about 100%. And the reason why is as follows for me. We've classified the eras of Earth from the very beginning to current. And we call the initial period the Hadean era, which means the hell era, because it's during this first 750 million years of our solar system that we refer to as the heavy bombardment. The solar system is a mess. It is constantly being impacted by very large objects. It is very much not a place that we ever thought life would be. Oops. We figured out that life was there during that time. Not a lot of it, not large-scale life, but a time in our own era that we defined as hell. In the reason being that it was, we said, there's no way that life could possibly live, have been evolving and born on this planet during that time. Oops. It did. And so if that can happen, if under the worst of scenarios, life can just come in, however that happens, another Nobel Prize waiting to be won, I'm going to argue to you, if under those worst of conditions we can come out of that, and we know that we came out of that, then why shouldn't it be the same everywhere else? The next step is F sub I, the fraction of intelligent life. Again, it's hard. Of course, human beings are, we like to think of ourselves as the dominant life forms on this planet. From day to day, as I watch the news, I wonder. I have dogs. I have golden retrievers. They have the intelligence of about a 3 or 3.5-year-old. We know of many dogs who know many words, can do many things. We know of pigs and dolphins and whales and all kinds of primates who can show us intelligence on varying levels. Certainly it does not reach our level of sophistication, but clearly they have an intelligence to themselves. One can wonder, okay, well, what would happen if time starts going to a very large scale? Well, maybe they'd win out. So again, we can hedge our bets and say, well, the fraction of life was 1, so I say we're at 40 billion now. I'll hedge my bets, and we'll say that's a rarer event. That intelligence really crops up. We look around ourselves, we look through history. Humanity is very, very young. Let's say 10%. You've got a 1 in 10 chance that a dominant life form is going to appear on your planet, that is going to become intellectual, is going to start civilization, which is what comes next. The fraction of those planets that actually form a communicative civilization, a high-level civilization like our own. Not just people living in small tribes and small villages, but a technological, advanced civilization, sort of kind of like our own and where we want to be. Again, at this point, like I said, we had 10% for the last thing. We're down to 4 billion. I'll hedge my bets. I'll say you got another 10% on that one. We're down to 400 million. This is sounding good. This is sounding very, very good. There are 400 million intelligent, advanced civilizations in our galaxy. But again, there's a problem. Lifetime. Many of the people in this classroom, I learned Spanish from my mother because she lived down here in Florida during the Cuban Missile Crisis, where they had to teach her to say, I'm an American, please don't kill me. And this is where I learned my Spanish from. We have, since the mid-40s, had the ability to way more than annihilate ourselves. And we've only gotten better at doing it ever since. We are an efficient species, if nothing else. And we live in an era where really all it takes is one terrifically stupid person with the power and the means to end it all. It's terrifying. It's terrible, but it's true. We've certainly had many cases of life. Look at Europe forever. They have just recently started to cooperate. And again, cooperation. For Europe, they've been warring with each other since written history began. This is not new for our species. We are a warlike species because we demand resources and information and technology. We're constantly expanding and growing. It's part of what leads us to people like myself, scientists, because we want more knowledge. We're greedy. We want more and more knowledge. We want the answers. Every time you give us one answer, we ask 10 more questions. And so it's part of our culture. For every good piece we get from that, and it's a very good thing, we also get terrifying things that come with it. And so we only know about ourselves as a civilization goes. And so we have to extrapolate, which is extremely dangerous mathematically speaking, and say, well, maybe all these other civilizations are probably like us. So how long do they get to live? How long is it that they last as a communicative species before, again, some incredibly arrogant, stupid megalomaniac destroys everyone? This is a tricky thing, because remember, we have only met the communicative civilization criterion for about 100 years. We are still infants. We have only just begun. Again, I see a lot of people in this room who are significantly older than me, who have seen enormous technological changes. I say I've seen enormous technological changes in my life. Holy crud. When I am 80 or 90, that's going to be a much better statement. But we've only been doing this for about 100 years. So even if we're really nice, even if we're very generous and say we're going to get 1,000 years, and that's the low shot. The doomsday calculation, the Armageddon calculation, says the human species will probably wipe itself out almost certainly within the next 9,000 years, in one way, shape, form, or another, no matter what. That we've probably got 9,000 years of life left. So maybe we'll go with 10,000 years. At that point, we throw that into the equation, 10,000 years out of the 5 billion we've been here. It's a very small fraction. All of a sudden, my estimate, where a moment ago we were at 40 million different possible civilizations, we're somewhere down in the order of 4. Womp womp. So, first and foremost, though, it says there were either at this time or at any other time in this galaxy, on our extremely conservative end, 4 civilizations. That means there's more than one. And that means we're not alone. And I have been very conservative for the most part in this. If I ease up even a little, if I say that we have gotten past this moment of technological infancy, this teenager type years of our ability to destroy each other where we just kind of go nuts a little bit, and we've reached a slightly, albeit only slightly, higher level of maturity, maybe, just maybe, we'll survive for a longer period of time. Maybe, just maybe, we won't have to worry about these problems anymore. And these civilizations can live for a long time. Even if I add an order of magnitude. For each order of magnitude I add, rather than saying, okay, maybe we last for 10,000 years, if we last for 100,000 years, now there are 40 civilizations in my galaxy. If we last for 100,000 years, now there are 400 civilizations in my galaxy. The room between us starts to shrink. We get closer and closer to each other. See, one of the big problems of there only being 4 civilizations in this galaxy is, first and foremost, we're probably the only one that's currently alive. The galaxy is about 8 billion years old. If my civilization only lives for 10,000 years, even if we go to that planet where that civilization once was, nice ruins. But no life. They're gone. They're extinct. It's over. We've missed them. Still, it's a thought to start to ponder ourselves with and start to look around and say, what's going to come next? So what I want to talk about for the rest of this is the fact that the game is changing significantly. Where I'm hedging my bets now, in 10 years it's entirely possible that someone will stand right where I am now and give you much better information. But here's a visualization of some of the data we've currently gathered from the Kepler spacecraft. What we see primarily in the circle is the orbit of Mercury. And we notice that most of the planets that we found are very close to their home star. We also find that most of them are very, very hot, as we see here. That's no good. We don't want a thermophilic planet. We want a planet that we can actually live on, an Earth-like planet as we see down there. But we not only need that, it also comes down to size. If I'm on too big of a planet, you're not going to be happy there. Too small isn't quite so bad. You're going to have mad ups. But we want an Earth-like planet, and that's turning out to be very problematic. The reason why is how we look for these planets. So let's look at a little bit more of this data. Again, here's a bit more of the Kepler data. I love these videos because they take a number where I can say we've seen about 2,500 planets at this point that we know of or that are candidates. It's a number. People don't really get numbers. Again, look to the politicians who scream them at you all the time. Visualizations work a lot better. And we can start to see here are all the planets that we know about if they were orbiting our own star at their proper orbits, at their proper inclinations as far as we have observed them thus far. As we start to move back, we start to say to ourselves, we've only just begun. This whole planet hunting game has only just begun. The first planet we really found arguably is in the mid-90s. That started to evolve in the early 2000s, and suddenly the floodgate has opened. And again, it is just opened. And now we're at about 2,000. So in a few years, in less than a decade, we've gone from 8 planets that we could say, yes, there are 8 planets, to 2,000. And I'm telling you again, scratching the tip of the iceberg. As time goes on, this number is going to inflate, and it is going to inflate rapidly as our techniques evolve. The problem so far has been, as we can see, most of these planets are extremely close to their home star. It's not a statement that that is the case of how things are. It's a statement of that's the way that we're currently finding these exoplanets. So we only have a few methods available to us in order to find these exoplanets. One of the first is very simple. It's the idea of a Doppler shift. We all know that as the ambulance comes towards you, the frequency goes up, the pitch goes up. As the ambulance goes away from you, the pitch, the frequency goes down. We get that very, very familiar sound that we've heard many, many times before. Light is going to behave in exactly the same way. As a planet is going to move towards you, the red object here, the star will move away from you. The star is where we're going to get our light from. As the star is going to move away from you, the light is going to get redder. As the star suddenly starts to move towards you, the light gets bluer. So first and foremost, this is really easy. That's an understatement. Where we can watch the lines go back and forth. Wait for them to get back to where they began, and you know the orbital period of your planet. But more so, we can look to this information and start to work out the mass of the planet, the mass of the star, as well as other information. The problem is we're beaten by resolution as always. We just don't have big enough telescopes. Please keep paying taxes. Support the NSF. We need telescopes. So speaking of those telescopes, we can try the old direct detection method. Rather than watching a wiggle and jiggle of a star, why don't you just look at it and get it that way? It seems a lot easier. Well, again, understatement. Because this is the idea of seeing a firefly next to a spotlight. The planet is going to be extremely dim compared to the giant star sitting next to it, which is going to make it very, very difficult for it to observe. Of course, we have done this more than once, more than twice. But it's still very, very hard. Again, one of the cruxes of this conversation I'm having with you tonight is to say we are in the infancy of this. We have only just begun. But in stepping foot into the water, we have found that it is nice. We have found that there is a lot of information there, and we are desperate to go deeper. We can see other direct detections. Fomalhaut, not quite so successful here. But what, again, we're looking for are Earth-like planets. And a few years back, I got to freak out when I read the news about Gliese 581d, just like everybody else. I'm a scientist, so it's probably a bit bigger. But again, we had said, all right, maybe, just maybe, we found a planet inside of one of these Goldilocks zones. This is what we want. We want to find a planet, again, where we have water that is liquid. That is our prime criterion. We want liquid water. For everything the biologists tell us, that seems to be the crux. Without that, you can go nowhere. Well, Gliese 581d was nice. But we found a few other interesting things since then. I want to introduce you to a bit of the exoplanet zoo that is growing at this time, because we're finding things that are very interesting. Growing up, we sort of grew up with Mercury, Venus, Earth, Mars. Okay, are similar terrestrial type planets. Most people, again, hopefully we have a better idea of their sizes. Mercury and Mars are quite small. Earth and Venus are similar. You got your Jovian planets, Jupiter, Saturn, Uranus, Neptune. And we say, okay, they're not terribly useful to us. But what about a planet that is made consistently of carbon and water, that is so close to its star and is under such pressures that it's entirely made of burning ice? This is a planet that is made of ice that is on fire. That wasn't so much expected. Possible, yes. Expected, maybe not. What else have we found? Well, there's the Kepler system. Kepler is Kepler object of interest. Again, from the Kepler space satellite. Here we have 5 planets stacked well within the orbit of Mercury. You could easily stack another 5 in and another 15 in without having any worries within the orbit of Earth. Imagine, again, Mercury is so close to its home star that its physics baffled us until the early 20th century when Einstein said, I have an idea. These are even closer, and there are 5 of them. Imagine how many other planets might be in the system that we have not yet detected. Now, these are not going to be planets where we're going to find life. They are going to be on fire that close to their star. But we want to say, if there are 5 there, how many more are farther out? We have this, which is the Centauri system. Again, it was not clear these are all animations. We have no pictures of these planets. This is the Centauri system. That should be a somewhat familiar name to people. The idea of Proxima Centauri, 4.26 light years away, the closest star system we have to us. There are 3 stars there, Alpha, Beta, and Proxima. And we finally, in the last year, detected a planet around that closest star system. Again, we want that lowest hanging fruit. These distances are enormous. At the velocity of our fastest object we've ever made, Voyager 1, at just less than 14 kilometers per second, talking about crossing Florida east to west in less than a minute. It will take us thousands of years to get there at that rate. Thousands and thousands and thousands of years. But it's still the closest star system to us, and there are 3 of them. And we found a planet there. This is good news. It is not going to be habitable for us. It is Earth-sized, but again, it's way too close to its star. Speaking of close, imagine if you're on this system. This is Kepler 36b and 36c. It's a somewhat Earth-like planet, magma, with a Neptune-like planet right next door. It's going to have a planet which will orbit around its star, and its closest approach will be about 5 times farther away than Moon. And Moon is not very far away, about 400,000 kilometers. This object would rise on your horizon from time to time during your year and be twice the size of Moon. Imagine that as a full moon for your planet. And speaking of close to your star, we found a planet that is very, very helpful for us. This is BD 48740. And it is a planet which is so obligingly vaporizing itself for us. Why? Physicists love it when we burn things, because we get to tell what you're made of. As I tell my students, back in the 19th century, we had our triumvirate of pyromaniacs, Bunsen, Kirchhoff, and Fraunhofer, who decided if they burned everything, they could determine what they were made of. Well, we have a planet that is saying, sure, I'll burn myself for you. And when we watched this, we said, great! Now we get to know exactly what you're made of. Awesome. Because otherwise we get to use a lot of shenanigans, light passing through your atmosphere to try and understand what's going on. No, this planet is falling into its star, slowly but surely. And the star is vaporizing the planet. This is a future that will actually happen most likely to Earth. Don't worry, you've got about 8 billion years. What else have we found? Ladies, we have a planet made entirely of diamond. We will not run out. We have what we call a carbon planet, which is going to be under such enormous pressures that we're going to take carbon, one of the most abundant elements in the universe, pretty much the 3rd most abundant element in the universe, and we're going to make a planet almost entirely out of it and put it under enormous pressure. Again, we've known for years, take a lump of coal, give it to Superman, diamond. There you go. Same idea here. Again, stuff that maybe science fiction had once written about, but now the scientists, not the science fiction writers, are going, yeah, we got that. We can do that. Hell, we found Krypton. Recently, we had Neil deGrasse Tyson over here on the right say, I found Krypton for Superman, so now we know where he lived. Awesome. We have even more interesting planets. This is the lonely planet, or the homeless planet. It's the idea we've had for a long time of vagabonds. Making a solar system is a messy process. It is not going to be clean. Early in our solar system, we might have had anything from 20 to 200 planets orbiting our star. Clearly, that changed. Things are going to happen. Some of them are going to fall into each other. Some of them are going to collide and form larger planets and new planets. Others might just get ejected right out of the solar system. We have now found a planet that is just lingering out there at enormous velocities all on its own. Not perhaps the best place to look for life, but all of a sudden, remember that Drake equation we were talking about? Where I said we were limited to stars? Not anymore. There are planets that aren't even orbiting stars. They've been launched out of their solar systems. They, again, although somewhat unlikely, could easily be places for life. We can form scenarios where we say, maybe there isn't a star nearby to provide the energy for life to form. But what if I have a highly active planet that produces a lot of its own internal energy? We have xenophiles that live at the bottom of oceans. We have xenophiles that live in places where biologists said nothing will ever live there. Oops. Again, scientists try to avoid words like always and never because they tend to bite us in the end. We try and always hedge our bets, which is why people are scared of this talk. But let's get to the meat. Why we're here. Gliese 581c. Here is one of our best bets. Here is a very, very Earth-like planet. But again, we need to have a discussion of what Earth-like means. So let's do that now. Here I've taken the Star Trek reference, which is fun for me. But we say we're going to label our planets in 3 different ways: HP, P, M, T, and HT. And we're going to say that these are planets that are going to be very cold, kind of cold, just right, hot, and oh my God, that's hot. We want to be in that nice, just right zone, where again, liquid water is going to be coming in. So what have we found so far? Well, when we plot these out, this is the result that we're going to get from all of our hard work. That we're looking for these green type planets. Again, look at Earth and Mars in the top right. There's our reference point. Up at the top is our legend for, again, our hot planets, our just right planets, and our cold planets. Unfortunately, we haven't done it quite yet. We have some wonderfully great planets. Again, some of these Glieses, some of these Kepler objects up top. But really, when we look to our report card, here is our 864. We are absolutely positive that these planets exist and that we know a lot about them. The problem is, this is the butter zone right here. And we haven't hit the mark yet. We have not found yet what we're looking for. The optimism here is that we have found some warm super-Terrans. Planets that are going to be a little too hot and where you would feel a little heavy because gravity is going to be a bit more than you would like. But there's nothing to say that life couldn't form there. We then go over from the ones that we are absolutely certain of to the 2,717 that we go, maybe. And that, by the way, when a scientist says maybe, they mean I'm pretty darn sure. But again, we hedge our bets constantly. So we have another 3,000 planets that we say, yeah, probably. Still, though, our butter zone remains out of luck. The problem is it's easier, as you might imagine, to detect a very large planet than it is to detect a very small planet. For a number of reasons, it pulls harder on its star. It will reflect more light from its star. It's just bigger. Earth is an itty bitty little planet. Go back to that video I showed you at the very beginning. We are very, very, very small. So here is the crux. We had to throw out 2 of our recent hopes. We just pushed them off the list. They didn't end up existing the way that we thought they did. But here are our best hopes. And basically, we're looking for a value here of 1. Again, our key on the top right says that Mars, where we will absolutely, please, be sending human beings sometime soon. We will start building colonies and civilizations there within the next 100 years. That's a 0.64. It's 64% Earth-like, as we might say. We have found objects which are more Earth-like than Mars. And it starts to show you how well we're doing. At the very far end, we have an 82% match. It's not great. It's going to be a hair big. You're going to be a little bit heavy. It's probably a little bit hot there. But again, I could throw you there and you would probably do just fine in the long term. So we're getting closer and closer and closer. Again, this data, as we look to the bottom right, whenever I give a talk, I try and give you that which is most up to date because this field is changing extremely rapidly. Every day there are new announcements. In my primary field, it can be a while before things really, really change. But Here is a very, very hyperactive field. And we've got a lot going on. Here's where we stand currently. Again, confirmed 867. Candidate, meaning again, probably, 2,717. And we've got another 188 in the wings. And again, this is from today. We have not yet been terribly successful at finding Earth-like planets, but what we have done is we've scratched the surface, and things have begun. So let's punchline this whole conversation. Because I can talk for an hour and have you walk away with very little. So what I want you to walk away with is there's not a doubt in your mind there's life in this universe. Because here's the deal. I told you there are probably four civilizations that may or may not have lived at any given time during our galaxy and our term here, in our tenure. But let's look at the whole. Let's look at the universe. Because here is a release from the Sloan Digital Sky Survey. It's the gold standard of surveying the sky optically as far as we have currently. We found about 500,000 galaxies and about 100,000 quasars actually at this point from that. This is not a simulation. This is real. Every object you're seeing here is a galaxy. And we're still close to home. As we pull farther and farther back, we move farther and farther back in time. The punchline you need to get here is that we have about 400 billion stars in our galaxy. There are about 100 billion galaxies in the universe. Perhaps there is not life currently living, again, intelligent life, in our own galaxy. But I would be absolutely astounded. And to quote the words of Carl Sagan, it would be an awful waste of space if all of this contained us, and that was it. Again, this map is not even nearly complete. As it rotates, these empty gaps aren't because there's nothing there. We just haven't looked there yet. To quote Armageddon back in 1998, it's a big sky. There's a lot of stuff. You might have heard a meteor, an asteroid that we missed that one, kind of streaked over Russia recently. Oops! We missed it, and it hit us, and we missed it. So again, this is a very, very challenging field. We as astronomers are hunting for fireflies at distances you can barely conceive of. And we are fishing through the noise in order to find them. Here is our entire observational universe. And again, those who are observing it over the STSS project. But again, if we go back to the numbers as I have presented them to you, if we look at the information that has been given to us by what we've currently gained in exoplanetology, if we look at the information from Kepler and from all the other data we've gotten, if we look to Frank Drake's famous non-scientific equation, but that can tell us interesting things, the probability seems extremely high. So a question comes, always. I'm going to head it off right at the pass. Where are they? And this is not my question. This is the question of Enrico Fermi in the 1950s, the famous Italian-American Nobel Prize winner who helped work on the bomb back in the 40s. A whole bunch of people at Los Alamos one day were talking about this, saying, oh yeah, it's probable. They're saying exactly the same things I am, with a lot less data. Some of the best and biggest brains on the planet are saying, absolutely there is intelligent life out there. And, Fermi looks and goes, so where are they? If you're so right, where are they? And the answers are depressing. Well, one, we could be alone. There's the rare Earth hypothesis. If you look at all of the conditions that are needed to make us, it's a laundry list. We need Moon. Moon is a planet called Tia that probably hit us a long time ago and formed Moon. Not only did we get a moon, we got a moon at the right distance, and it's enormous. And we need it. It balances our planet. It maintains a constant rotation. It maintains a more or less constant climate on this planet because we won't fall off our axis. We need a large planet like Jupiter to act as a shield to protect us from all of the debris coming in from the outer solar system. We need a sun that was just right. We need a planet that had so much water on it. We need to be at just the perfect distance from sun. And the list goes on. And so some scientists will say it's so hard that we're alone. Gosh, that's depressing. Let's go with another depressing thing. They don't want to talk to us. We smell bad. They are so advanced. They are so intelligent. It is much like us looking at one of our children in the sandbox. We don't really inquire as to what they're doing. We say, oh, that's cute. And then we walk away. When I look to my dogs on a daily basis, I do talk to them, I won't lie. I carry on full-blown conversations with them. But I don't really go, so what are you doing? How is that scratching that you're doing right now? No, it's the same idea where if you reach a certain point in your development and you're so intelligent and you know so much, you look at us and we are backwards. We know nothing. Why would you even deal with us? Okay. That's a little bit depressing too. More depressing, the zoo hypothesis, or as Star Trek calls it, the prime directive. Don't mess around with lower intelligences. Okay. Seems like a good idea. You come here with all the best intentions. We're currently in all kinds of problems. One of our biggest problems is we don't have enough energy. Our energy problems are leading to climate change, all kinds of other issues. So they come and give us an infinite supply of energy. We'll never, ever run out. What will we do with it? Kill ourselves. Almost inevitably. It's the idea that maybe you teach us a better way to fish. We kill all the fish. And now we're starving. You can help us on one hand, and a civilization could easily come down and have the best of intentions, but we know the road to hell is paved with those intentions. And so it could easily be that alien civilizations have gone through this before. They have caused other civilizations to die and said, okay, that wasn't so good. Let's not do that anymore. And so they just leave us alone. As if we are locked in a cage in a zoo. They look at us, maybe even they come and visit us and check up on us. But if someone's going to launch a nuclear strike across the planet, they're going to, well, that sucks. And move on and not do anything about it. Because interference on any level might just lead to the same problem anyways. It could be that interstellar travel is too hard. These distances between our stars are titanic. Again, we looked at just taking a trip around the largest star. It takes a millennia. Think about what we were doing a millennia ago, when we didn't even have ideas of flying machines. It might turn out that traveling that distance between the stars is literally just too hard. That the laws of physics don't allow for it. That's not looking like the case more and more by the day. But it could simply be the energy requirements, the technology, the wherewithal is too much that no civilization ever does it. We can also say again, civilizations die out. That they were around for a long time. Maybe even they formed an enormous galactic empire and an alliance rose up against them. And then they just died off. And that was it. And then later on, 1,000,000 years later, here we are and we arrive in nice ruins. We need to be in the right time at the right place. So this is a very hard game we're playing. Because we're constantly trying to broadcast this information. We're constantly trying to listen. And so far we've gotten nothing, but we've only just begun. It could easily be, and probably is, that there are so many laws of physics that we do not yet understand. Things like being able to communicate instantly over infinite distances. Currently, scientists, of course, say, no, that's not possible. And if any of my students ask me that, it's exactly the answer I would give you. No, that's not possible. But 200 years ago, a lot of what we're doing, again, the scientists, the very good scientists who have said, no, that's not possible. Things change as time goes on. Maybe traveling through the skies is very easy. Maybe communicating through the skies is very easy. Maybe there's a lot of communication going on all around us. Again, we're just a little slow. And we haven't figured it out yet. How to listen in on this cosmic radio station that's saying, by the way, we're all here. If you'd like to join in the conversation, dial. No, we just don't know what's going on yet. We have lots and lots of ideas as to why we haven't met these aliens yet. I was in the last minute adding the one most important capstone piece to this story. Alien abductions. Oh boy, here we go. There is not a single shred of credible evidence anywhere, anytime, ever about having aliens visit us. Again, trust me, every scientist in the room, I bet every person in this room, I would line up and pay whatever you want to have a 5-minute conversation with an alien. I'm a scientist. I've got questions. We would love, as the scientific community, to say, yes, this person was definitely beamed up by Scotty. Something definitely happened, wrong or right, and they were brought back, better or worse. Because one way or another, we can learn something from that. Even if you couldn't bring anything else back with you, you could say, they look like. The biologists have a new idea. Or their ship was like. Or I heard this, or I saw that. We get information. And we can start building on that information. The problem is it's all anecdote. And again, the litmus test of science is extreme. We do not take anecdotes. We do not take hearsay. We do not take, I was traveling along one night on the dark highway. You have to have proof. And that's the problem. No one has at any point been able to offer literally any proof. Not even a shred of it. Not even something that we go, well, kind of, maybe, and hem and haw about it. We're very good at that. No, there is none. And so we literally, at this point, have nothing to go on. Enrico Fermi's question remains extremely poignant. Where are they? We don't know. By the physics, by the math, by the probability, they should exist. But we have never seen them. We have never heard from them. As best as we can tell, they might be very good at this. They have never visited us. Thank you.
Thank you very much, Dr. Gobeille. We have time for some questions. Don't be shy. It would seem to me that if one were looking for life and working with these equations, it seems like you would find the most probable would be these moons that have frozen water and
Absolutely.
water beneath the frozen ice.
Absolutely.
Rather than Earth planets at all.
Absolutely. Absolutely. And there's
much emphasis being placed on trying to identify those kind of...
Yes. The problem is they're very small, and thus they're harder to detect. But again, we can sometimes, as these large planets are passing in front, so basically we have their star, you're the observer, with the star, the planet passing in front, and then the moon will move around. And we'll notice perhaps, if we're lucky, it's very hard, but we have detected some moons of these very large planets if they're very close, and we can look at their atmospheres. I can tell you that, for example, Europa and Titan have more water than we have here on Earth. It's not so accessible, it's not so easy to get at it, but they have way more water than we have here on Earth, which is actually intuitive. The water should be in the outer solar system, not the inner solar system. Comets hit us. That's where we got our water from. Those moons are really the gold mine. And everybody, I think, in this game knows that. The problem is we're having a hard enough time detecting Earth-like planets, Earth-sized planets. The moons are even smaller. It's on our hit list of things to do. Again, I shouldn't say ours. That's not technically my field. But again, the exoplanetologists that I talk to, they're saying, yes, we know the moons are an untapped gold mine, but we need better telescopes. We need better techniques. Those things are totally coming, and they're on the horizon. We're just, again, it's always iterative. We're moving closer and closer and closer. We'll start finding, again, I could easily place a bet that I will win 5 years from now, we'll know about one on that scale in terms of an Earth-like planet. It might take another decade after that to find a moon of that type, because again, these large telescopes that we're going to need, again, space-based telescopes like the Jim Webb, which won't be going up until 2018, we've got to wait. We have to be patient in this field, unfortunately. But yeah, the moons are going to be just a terrific gold mine. They should have a lot of water. They should be very, very numerous. And because we have lots and lots of Jovian planets in the right Goldilocks zone around their planets, or excuse me, around their stars, we hope, like Jupiter, that they've got literally dozens of moons, because each one is a new probability. We go, great. It's like adding more tickets to some kind of a prize fair. You know, you're going to win. So we like that. Absolutely. Sir?
What methods do scientists use to locate the water on other planets?
It's tricky. Again, it's that idea I mentioned that we need to, well, if the planet vaporizes itself, that's nice. That's the easy way. It doesn't help us much. By the time we get there, the planet's already gone. Again, what you do is, it's very challenging, but you wait for the planet to move in front of the star. The light from the star then passes through your atmosphere, and we can detect the fact that there should be the water line, the clouds. If we can see that on the planet, we can start to infer, again, that is the right word to use, is to infer that there is water there. But I need to be very, very clear. We've never even really seen the shape of a star. We've seen a few of them. But to us, almost every object that we look at, star or planet, other than within our own system, is literally a point. The smallest pixel you can imagine, that's what we get. When we look, there are a few exceptions. That number is growing by the day. But if we're looking at planets, it's a pixel. And so that resolution becomes a very challenging thing. But sometimes we get lucky. We can see the light passing through the atmosphere. When light passes through a gas, it can tell us about those characteristic properties of that gas. And so we can take a spectrograph of that and say, okay, there's maybe water there. And that's how we start to go about that. But yeah, that's tough. What else? Ma'am?
Did you say there was 40 billion stars?
400 billion stars.
400 billion.
That we know of. So there are more, actually. That number should just grow. Even if we look at our own within 10 parsecs of Earth, again, it's about 30 light years around Earth. That number has been going up. Even this extremely close neighborhood around us, we keep finding things that we haven't seen before. Because some things are very small, some things are very dim. We can find things like neutron stars and black holes, which more or less don't give us any light. You have things like white dwarfs, which are extremely hard to see, even nearby from time to time. We keep finding more and more. But that 400 billion number is pretty good. Depending on who you talk to, they might even go as low as 100 billion. That number in front isn't quite so important as much as to say there are 10 zeros there. And that's or 11 zeros in that case. That's the important point. Sir?
You were using the Drake equation for Swiss galaxy.
Yep.
Factored to the universe.
That's the point. That's the point. That is the point right there. Again, even if we say every galaxy just gets one, and that's us, 100 billion galaxies. That means there are 100 billion civilizations out there. That's why even if you don't want to go with the Drake equation, even if you want to say, you know, Dr. Gobeille, we could take more conservative values. We could really, really put this up against the wall and say we're probably the only civilization in this galaxy. I go, that's fine. There are 100 billion other ones. So we're not alone. And that's what I mean. To have those 100 billion galaxies and have our one planet around our one star having one intelligent species, scientists don't like flukes. We don't like coincidences. Things should fall into patterns. Flukes do happen. Weird things do happen. But this experiment of humanity, it should not be one of those things. This experiment of large-scale intelligent life should not be one of those flukes. You should more or less expect it everywhere. Just like anywhere we look on Earth, even when we say there shouldn't be life there, every time we say that, we eat those words. We've done it again and again and again. The biologists these days just don't even talk about it. Because anywhere they go, they know they're going to find something. So the most recent life we found was at the bottom of a toxic lake. We found mushrooms growing in Chernobyl. They're thriving there. They love the radioactivity. Life, as some have said before, will find a way. And so that is a perspective I tend to take to say, again, that Hadean era argument I made with you, that life just seems indomitable. It's going to do it one way or another. Give it the hard way or the easy way, who cares? It's going to get it done. And so for us to be alone with just the enormity of the universe is strange. And we don't like strange in physics. There are plenty of strange things, but it means we don't understand them well enough yet.
Okay, one more question. Is there any O stars in the Milky Way?
Absolutely. Tons and tons and tons. In fact, if you look to any picture of a galaxy, I mean, for the most part, we tend to go with the pinwheel galaxy. But again, here is, oopsie, nope, wrong stage. Let me do, whoop, maybe, nope. I'm having a hard time here. There we go. Dan, can you lower the lights just a smidge? When we look at galaxies, what we tend to see are the arms, again, spiral galaxies. We tend to see the arms, but what we're really seeing here are what we call tracer stars. These are those enormous O and B class stars. They are so large, they dominate the scene. What you tend to see when you see one of these galaxies, ignore the middle, it's a whole different story, but the rest of it, the vast majority of it, we say, okay, what do we see? We see the arms and they're blue. You tend to see red with them. That's another effect. The blue is the O and the B class stars. But in fact, if I look across this whole thing, you look at this image and you're going to say there are more stars along the arms. I go, nope. It just appears that way. Because along the arms are where those stars form. And OMB class stars form very quickly and die very quickly. And so you see them where these pressure waves in the galaxy build up, and they become tracer stars. It's the big bright thing that draws our eye. But there's in fact just as many stars in this region here where it doesn't look that dense as there are here, where it actually looks much, much denser. It's about 5% more in the arms. But again, we say, don't worry about that. That's just because there's a bit of star formation in there. But yes, they're all over the place. And they're the big ones that go boom, by the way.
And on that note, let's thank Dr. Gobeille.